Welcome back. Fasten your seatbelts. This one's a little bit of a long one. Let's go. So we're going to recap briefly on formulating those hypotheses, but I'm sure you're already an expert, always drawing that picture. We're going to talk about level of significance, choosing a test, finding critical values or those cutoffs, calculating the test statistic, stating the conclusion, and we'll look at some hypothesis testing in R. So a quick recap on hypothesis formulation. Hypotheses always come in pairs. We have the null and alternative. The statements that you make with a hypothesis are always about the population, and as such, we only ever use mu and never x bar. And hypotheses can be formulated to test either a one-tailed, which has no direction, you're just testing if there's some sort of a difference or an effect, or a one-tailed, where there is an assertion of direction and difference, like a greater than or less than. So remember, we can have a two-tailed, which is testing for a difference, whether greater than or less than, we're not making an assertion, and we can have a one-tailed test where we are testing for less than or for greater than with left and right, respectively. So we have our step one, and drawing the picture. That is my own little add-on there, but seriously, draw the picture. Level of significance, alpha. Remember that 95% confidence level for our confidence intervals? What did that mean again? Means that 19 out of 20 or 95 out of 100 times, if we were to repeat our sample and calculate a mean, 95% of those 100 means would contain the true population parameter mu. But that also means that 5% or 0.05, the proportion of the time that we are going to fail to capture the truth, that we are going to miss it. The complement to the level of confidence we want is the level of significance. So level of significance is really this kind of question of how much of a risk are you willing to take about being wrong if you reject the null hypothesis. With a level of significance of 0.05, or that 95% confidence level, they're the complements, remember, you are risking being wrong 1 in about 20 times, about 5% of the time. Now these are some common level of significance, like the 0.05 or the 0.01, and sometimes you use that more strict 0.01 in higher stakes outcomes, like in medical testing. And sometimes you see this 10% or 0.10, but it's usually not accepted. Significance levels are denoted as alpha. That's what this symbol is right here. So if we wanted a 95% confidence or 5% level of significance, we would write alpha equals 0.05. So here in this area, if we wanted to be 95% confident or at a significance level of 0.05, we would have 95% of all the sample means, if the null were true, would fall within here somewhere. But that means that 5%, 2.5 over here, or 2.5 over here, we would expect to be extremely high or extremely low. Now when we are doing a hypothesis test, we are going to deem these areas, this extremely high or this extremely low, too extreme and unlikely enough, basically. It's so unlikely that the chances of seeing this particular sample mean, if it's way up here or way down here, is about 5% or less. So deciding that 0.05 level or 0.01 level is basically deciding where you are going to put this cutoff value, that we consider this value over here, from here up or from here down, that is extreme enough that we are willing to reject that null hypothesis, acknowledging that we could be wrong 1 in 100 times for 0.01 or 5 in 100 times for 0.05. When you select a significance level, and by extension your confidence level, you are defining the boundaries for what will be considered unlikely enough or extreme enough, extremely low or extremely high, for us to reject the assumption that we live in this null world. So imagine that there is one school that had an average star test that was way down there, 2.5, when the average should be 10. Do you think that everything is fine and it's just a fluke? That they just happen to have such a low average? Or would you reject the idea that everything is okay, that null, and maybe want to investigate further? Maybe there's something wrong with that school district. Look at an example about how unlikely is unlikely enough. Say you want to know whether getting tutored in statistics actually has some sort of an effect on your class grade in the GPA scale. The average grade in statistics course is 3.0. So if that is the status quo, we are going to assume in the null world that tutoring has no effect, so mu is going to be equal to 3. Our alternative hypothesis is going to state that mu is not equal to 3. But notice in this particular example, it just says an effect. Even though we're talking about tutoring and we would hope that it would increase your grade, we are not making any assertion of which direction it is. We are just saying a difference. Using what you know about sampling, remember that even if the tutoring has no effect, that tutoring does not change your grade whatsoever, Do you think that your sample mean will be exactly 3.0? No, there's going to be some variation. So we want to know, what is 3.0 enough for us to conclude that tutoring has no effect? What if your sample had an average GPA of 3.4? Do we reject the null? Or what if the sample had an average of 2.9? Do we reject the null? How extreme is extreme enough? Let's say the sample mean that you calculated was 3.4. How likely is it that that observed sample mean that you calculated is an extreme value in the null distribution that we would expect less than 5% of the time, or a truly different value from a different distribution, an alternative distribution? In this case, maybe people who are tutored are actually different from people who are not. Again, always assuming that the null is true. Average GPA for even tutored students is going to be 3.0 because tutoring has no effect. We're assuming the null is true. If that null were true, we would expect sample means to be within a certain range, let's say 2.8 to 3.2. There are ways to calculate this, but I just made these up for the sake of the example. So if this were the case, how likely is it that I get a sample that is less than 2.8 or greater than 3.2? If we're testing at the 95% confidence level or significance level of 0.05, what is the probability that I see a sample mean that is 2.8 or less or greater than 3.2? Basically, what are the chances that I get a sample mean that is way out here? If the null were true and we set our alpha to that 0.05, the chances of getting a sample that is lower than 2.8 or higher than 3.2 is 5%. This would be a fluke under the null hypothesis. So in this case, maybe you ended up sampling a group of students who were already going to get a high grade anyway. You just, by random chance, sampled a non-representative sample and you got this fluke. Speaking of flukes, here's some wisdom from Kevin Malone. Here's a piece of trivia. A fluke is one of the most common fish in the sea. So if you go fishing for a fluke, chances are you just might catch one. This is from The Office, Season 8, Episode 11, called Trivia, and when I heard this, I was like, I'm putting this in my PowerPoint. And it's somewhat true that flukes do happen. How do we know if we are that fluke? Unfortunately, in the real world, we only ever take one sample. How do we know if our sample is one of those 95 that's correct, or one of those 5% that's too extreme and incorrect? Because we only ever see this. How could we possibly know that we're one of those ones that's out here, that that sample mean you got was actually just a fluke, and if you did it again, you'd actually get something that was failed to reject? Sadly, for the most part, we can never know for sure. This is why we have to acknowledge our p-value. It's the probability of randomly getting one of those extreme cases if the null were true. Maybe it's just an extreme null value. Maybe I just took a sample of people who would have done well without tutoring anyway, some overachievers. I see you out there. It could just be one of those extreme cases we expect to get 1 in 20 times, that alpha of 0.05, that 5% chance. Maybe instead it's from a different population, the population of those that got tutored, and their averages are higher than those who are not tutored. What is more likely? That you get one of those rare 5% extremely high means from the null, the tutoring has no effect, world, or that you get a reasonable mean for an alternative world in the tutored world? This is the essence of hypothesis testing. There are a lot of different types of hypothesis tests out there, but this example highlights the essence of trying to determine if a certain result is a fluke or some sort of real difference, all based on how likely something is. Choosing a statistical test. Which statistical test should you run given your data? Here are just a few. There are many, many more out there, but we will be covering these for the rest of the class. Now, this is just a helpful chart if you want to get ahead and see what we're going to be covering. But we have the statistical test itself, the outcome variable, and the other variable if there is one. And this is, it says language, but it's basically saying exactly what the test is actually doing. It's trying to test a relationship or a group comparison and such. And then some extra notes here, so give that a little look over. Regardless of which statistical test you run, you are going to end up with a test statistic. This is the number that you are going to compare to those critical values and those cutoffs. A test statistic is a standardized number that you compute from a sample. And we've done this before when we did our first little z-tests. Remember, we were calculating the z-value for a mean rather than a person. So that's what we're doing here. We're also going to do the same with t instead of z because sigma is unknown. We then compare whatever comes out of this equation, this t-stat or this t-stat, we compare that to our critical values, which leads us nicely into finding the critical values. The critical value is your cutoff value that you will use to determine if a test statistic is extreme enough or unlikely enough. Is it far enough out here that the chances of seeing it are less than 5%? Now, critical values come from the standardized table, and it depends on if you know your sigma, for example, you'd use z, or t for unknown, and there are other types of critical values for different types of tests, but we'll get to those later. A reminder, you've already looked up some critical values to calculate confidence intervals. So the critical value tells you the value associated with a certain level of significance, and by extension, of confidence. So remember, let's say that sigma is known and we get to use the z distribution. What would be the two values you would put to get a 95% confidence interval or the 5% out on the sides? 1.96, our old friend 1.96. So again, here are the reasonable values, the reasonable mean values that we would expect if the null were true. And here are the extremes, extremely high or extremely low. Let's do an example to see how all this works. Let's look at this example we did a few lessons ago. A random sample of 25 college graduates revealed that they worked on average 6 years at a job before being promoted, with a standard deviation of 1.3 years. Compute and interpret a 99% confidence interval for the mean number of years worked at a job before being promoted. So here is all of our information. Now, how high or how low do you think your test statistic or observed mean would have to be to reject this null hypothesis, that the average number of years it takes to be promoted is 6? How much further out would it have to be for you to say, no, that's not the case in this situation? How high or how low would your test statistic that you calculate have to be in order to reject the null hypothesis that on average it takes 6 years to be promoted? Maybe you think it's more, maybe you think it's less. But how high does your test statistic have to be for you to say that no, it's actually different from 6 years? In this case, we've already looked up our critical values from our last example, and it's plus or minus 2.792. Now, you have to get a test statistic that is either greater than 2.792 or less than negative 2.792 to be able to reject that null hypothesis that on average it takes 6 years to be promoted. Now, the other way you can look at this, that is the standardized t-values. Then you're going to compute that test statistic and be able to compare it to this. But it's also nice to see it back in the raw form. So here, because we create that 99% confidence interval around it, we actually also know in the raw scale how high or how low it has to be to reject the null. Here it would have to be greater than 6.73 years or less than 5.27 years for you to reject the null hypothesis that on average it takes 6 years to be promoted. Now, just a quick refresher, how do we go and find those critical values with the t-table? We need to get our degrees of freedom, the level of significance that we're testing at, and know whether it is a one or a two-tailed test. We've looked at the t-tail before when we were working on creating confidence intervals. Then we only looked at that proportion in two tails combined area, this one right here, which distributes the alpha level that you want, that 0.05, on two sides. So it's going to put 0.025 and 0.025 on each side. Or you can also think of it as 2.5% and 2.5%, which equals that 5% for 95% confidence. If we were running a two-tailed test, we use the same row as before, but if we were running a one-tailed test, then we have to look at that row right up here, where all of that 0.05 is lumped onto just one side. Looking up a critical value for a one-sided test is the same as a two-tail, but you're going to be looking in a slightly different column. And just keep in mind that instead of distributing that 5% on both sides, so 2.5%, 2.5%, we amass it all onto just one side. And we lump it all on the direction that we're looking for. So for a greater than right-tailed test, we put all of that 5% up here. And for a left-tailed less than test, we put it all on the bottom. So for one-tailed test, you will always only have one critical value instead of the two positive and negative ones. Let's try looking up these critical values. These are the examples from our last lesson of hypotheses and formulation, which you've already hopefully done. Pause me for a second and go and find the critical values associated with these examples. I'll be here when you get back. Number 1, an emergency room advertises a wait time of 10 minutes, but you believe that it's longer. And we have a sample size of 20 and are testing at the alpha of 0.05. So we already did our hypotheses for this. We think that it's a longer than 10-minute wait time. So we can draw our picture, and we know that we're looking on the right side. And because of that, we know that our t critical value is going to be positive, because anything above 0 is positive, anything below 0 is going to be negative. So let's go and see where we got this 1.729. Now we're looking at the proportion in one tail, because we are running a one-tailed right-sided hypothesis test. So we have 0.05 is the level we're testing at, and we're looking in the right column, the one-tailed, and we're going to go down, and we're also going to look for our degrees of freedom, which we had 20 people, 20 minus 1 is 19, so we find 19 and come across, and we find our critical value of 1.729. Number 2, a psychologist believes that watching 9 or more hours of football a week reduces men's self-esteem. The population of men score an average of 40 points on the self-esteem questionnaire. Here we have a sample size of 25. We're testing at the 0.05 level. Remember, our hypothesis was that the average of men's self-esteem who watch more than 9 hours of football is going to be less than 40 points. So mu is less than 40. Because of that, we know we're doing a one-tailed, left-sided over here, and because of that we know that our t critical is going to be negative. Remember, the t-table does not have negative values. It's up to you, drawing the picture, to know if it's going to be a positive or a negative. We're looking in the same proportion in one tail row up here, and we're looking for 0.05 again, so we're going to stay in this column. We're looking for degrees of freedom. We had 25 people, 25 minus 1 is 24. So we look right here and we find positive 1.711. But because we are doing a left-sided test, we know that it is negative 1.711. If you put a positive instead of a negative, usually this will give you the wrong final result. So be vigilant and draw the picture. Draw the picture. It helps. Number 3, it's suspected that behavior modification will have an effect on the average number of sodas a person drinks in a week. So have an effect, that is not any sort of direction. It's not saying increase or decrease. It's just going to be different, have an effect, so we know it is a two-tailed test. Two-tailed tests, we're going to have 2 different critical values, the negative one and the positive one, and you've already been doing this for confidence intervals. So if you go and look up on the table, we are going to see 2.20 positive and negative for this example. Now that we have all of our critical values, it's time to compute the test statistic. We're going to compute the test statistic, and we can then decide if we're going to reject or fail to reject. We can also figure out the p-value, but that requires R, which we'll get to later. If our test statistic falls in our critical regions or past that critical value, basically in those far out tails where it's unreasonably high or unreasonably low under the null world, we can then reject the null hypothesis. If we reject the null, we can say that the p-value was less than our set alpha level. Let's say we had 0.05, then we say the probability of observing this, if the null were true, is less than 5%. It states that though we could incorrectly be rejecting that null, the chances of that happening are less than 5%. But before we can determine if we can reject that null hypothesis, we actually have to calculate the test statistic. So let's go look at that. So try it! Find the test statistic for each of the following scenarios. Does it fall within the critical region? Now pause me and go give them a go. Number 1, an emergency room advertises a wait time of 10 minutes, but you believe that it is longer. We've already got our critical value, and we know it's positive and goes on the right side because you drew the picture, and because we think it's longer, so that is going to be a right-tailed test. So we put that right here. Take all of our lovely information here, get our sample mean of 13 minus the proposed mu, 10, divided by our standard error, we get 10.32, which is a huge t-statistic. It's going to be way out here, so we know right away that we can reject our null hypothesis. Number 2, the football one, where if you watch too much football, it lowers your self-esteem. If the average is 40, but you go out and calculate a sample mean of 39, do you think that's going to be significant? Do you think that's having that big of an effect on your self-esteem? Well, let's find out. Let's standardize. We have our critical t-value here, negative 1.71, and we only have 1 because it's a one-sided test. We go and calculate our t-statistics by taking 39, the sample mean that you calculated, minus the mean that is the national average, 40, divided by 6.9 divided by the square root of 25. This is our standard error. And we end up with negative 0.72. Now, if you drew your picture, you would see that that is not past our critical value. It's inside the realm of reasonable means in the null world. Remember, it's not going to be exactly 40 every time you take a sample, even if there's no effect. It's going to be a little high or a little low. And in this case, 39 was just a little low, and it's not low enough for you to say that football lowers self-esteem. So here we failed to reject the null hypothesis. There is no real effect of football on men's self-esteem. And again, I translated these numbers from the standardized negative 1.71, that t value. I translated that also back into self-esteem points. So if the average that you calculated, or if the average that you went out and got from your sample was less than 38.4 points, it would have been significant in this example. Also, our 39 points, this is the translation of it, right? Negative 0.72, which is not big enough. It's not big enough in the raw score or in the standardized score because they're the exact same thing, same message, just in a different language. So either way will give you the same answer of failed to reject. Football does not lower the self-esteem. Number 3, behavior modification in sodas again. You go out and get a sample of 12 people and you get a sample mean of 4 with a standard deviation of 2.5. Go and test. In this example, we have 2 tails. Remember, because we're just saying doesn't have an effect. We don't know if it'll increase or decrease. So we have our 2.20 here and our negative 2.20 here, with our 8 sodas right in the middle. Or remember, the t-value would be 0 for the mean. Now, if we go and calculate our test statistic, we take 4, the sample mean that you derived, minus the 8, which is the average, divided by the standard error, and we end up with negative 5.54. Now, where does that end up on our lovely drawing that I'm sure you did? It would be over here, past this negative 2.2, and it's in our critical region. So yay, we get to reject the null hypothesis that behavior modification has no effect on the number of sodas consumed, meaning it does seem to have an effect. Again, I translated these standardized numbers, this 2.2, I translated that into sodas. And if you drank more than 9.59 sodas or less than 6.41 sodas, that would be enough of a change from 8 to conclude that this is statistically significant. And we would reject the null hypothesis, reject the premise that behavior modification does nothing to the number of sodas you drink. So these p-values again. A p-value is the probability of getting the calculated test statistic or a more extreme number if the null hypothesis were true. Remember, we always work under the assumption that the null hypothesis is the truth. The smaller the p-value, the greater the likelihood that the null hypothesis is false and that you can reject it. In practice, statistical software like R tells the exact p-value, but the decision using critical values to determine if the probability of a fluke is less than 5% will result in the same conclusion. The rejector failed to reject. Stated conclusion! We're almost done! With this part at least. When we reject the null hypothesis, we are saying that the probability of seeing this result, this certain sample mean, if the null were true, is low enough, less than a 5% chance, that we can reject the idea that we live in the null world. We can conclude there is a statistically significant difference. Something is statistically significant if we are able to reject the null hypothesis. You might have seen or read before the results were statistically significant at the 0.05 level. When we fail to reject the null hypothesis, the results are not statistically significant. The x bar, or that mean that we observe, is close enough to the null that there is no statistically significant difference. Basically, it's a reasonable value under the null world. If the p-value is greater than 0.05, for example, we are saying the probability of seeing this x bar, this mean, if the null were true, is higher than 5%, and we don't want to go that much higher. After all of these hypothesis testing steps, you can finally come to the conclusion whether you reject or fail to reject something. Now this form right here is called APA notation for the American Psychological Association. Depending on what your field of research is, you might report this a little bit differently, but for the sake of this class, I want you to report things in APA. So here we have T, which is actually letting us know what kind of test we did, and we're going to learn more about that in our next few lessons. Here, though, is the degrees of freedom. So if we had 19 as our degrees of freedom, how many people were in the study? in this example 20. Then we say equals a particular test statistic. The test statistic is the one that you calculated. And then we say that p is less than or greater than 0.05, depending on the outcome of the results. So this was from our hospital wait time. So again, we're saying that we did a t-test. We had 19 degrees of freedom. Our t-statistic was 10.32, and it was significant at the 0.05 level. Technically, real APA notation gives the actual p-value rather than just the greater than or less than symbol, because statistical software like R will give you the p-value. The only reason that we still do this greater than less than and looking up critical values is for teaching purposes and for stats classes like this, because that's not what we would do if we were analyzing some real data. Rather, it would look something like this, where we would have T19 equals 10.32, so that's all the same, but now we say P is equal to whatever that actual p-value is. Now here, there is an actual number here, it's just that it's incredibly small. There's just a lot of zeros, so there's something over here. There is a probability still that this could still be seen under the null hypothesis. It's just a really small probability, and we just round to 2 significant digits. Now that we know all of the steps of hypothesis testing, yay, we made it. We also now know that we can sometimes make mistakes. Our p-value is kind of telling us the probability of making a mistake and being wrong. There are 2 main types of mistakes, called type 1 error and type 2 error, and that is what we're going to be discussing next. See you there. Bye. Hypothesis testing in R. Instead of looking up everything on the t-table, you could also use a function called qt in R to find the critical value. Two-tailed test, we need the positive and negative values associated with that. So you could write either of these 2 functions where we call qt, we specify the proportion that we want. This one is associated with 95, this one is with 99, and we tell it the degrees of freedom. And it will spit out 2 numbers, which are the critical t-values associated with these specifications. You could also ask R to tell you the critical t-value associated with the right-sided test, so there's only going to be one, and that one's even easier. There's only one number, and you say 0.95 or 0.99, depending on the level of significance you want, and then you also give it degrees of freedom, and it will tell you the critical t-value associated with that. If you wanted to do a left-sided test, you also use qt, but now you're going to specify either 0.05 or 0.01, because we're looking for that little part at the bottom. And that will give you the 95 or the 99 critical t-value associated with the specifications that you give it. Here is our wait time example again. This is all the information, and I'm going to tell R what everything is. I'm going to ask R to give me the critical value associated with the 95% confidence or 0.05 level of significance and my degrees of freedom. And it will tell me it is negative 1.729. Now, all I have to do is type in that little bit of code, that equation that takes the sample mean minus the population mean divided by the standard error, and it's going to give you a number. You compare this number to this number, and you can make your conclusions. And this will give you the same answer that we had before, which is to reject the null hypothesis. The wait time is longer than 10 minutes. Here's our football and self-esteem example, which was the one-sided left-tailed test. So again, we tell R all of the important information. Then we ask R to tell us the critical value associated with the left-tailed test. So here we would type 0.05 instead of that 0.95 that we did for the right tail, and tell it the degrees of freedom, and it will spit out our negative 1.71. That's our critical value, the same one that we found on the table. Now we take all of our known information, put it back into that same line of code to run our t-test, which is just sample mean minus population mean divided by standard error, and we get the same negative 0.72. So we have the same conclusion. We failed to reject the null hypothesis. And lastly, here's the behavior modification and soda example, which was a two-tailed test. Again, we tell R all of the important information. We go and ask R for the critical values associated with a two-tailed test with our degrees of freedom. And we put all of our information again in that one line of code to actually get our t statistic. And it will be the same situation where we reject the null hypothesis. And lastly, remember how I mentioned earlier that instead of just reporting greater than or less than, R can actually tell you the exact p-value. We can ask R to do that by using this function called pt. Now what we do is we call the function pt, and then we tell it what our t statistic was. There's one important thing. We have to write negative ABS, which means absolute value. It's going to take the absolute value of whatever your test statistic was, because it can be negative or positive depending on if it's right or left-sided, but we don't care about that anymore. We just care about the proportion. So we use this absolute value of whatever your test statistic was, and then we're going to put a negative sign in front of it. I know it's a little bit weird, but it gives you the right answer. And we tell the degrees of freedom, and it will spit out the exact p-value. Instance, the p-value was 0.000000. There's a value at the end of it somewhere, but for us, we can just call it 0. Next is that football self-esteem example. Now we would put in the negative 0.72 was the t-statistic we calculated. Remember, it was not significant. We're going to put it in here, and the number that we get out of it is 0.24. Now what does that mean? That means the probability of seeing a sample mean of 39 for self-esteem, if the null were true, there's a 25% chance that you would see that sample mean. So we would fail to reject again in that case. And lastly, we can get the p-value for our two-tailed test. This code's a little bit different now, but we're still going to be using PT, and we put the absolute value of our test statistic in there, tell it our degrees of freedom. We also have to tell it that the lower tail is true, and we are going to multiply it all by 2. I know it sounds a little bit complicated, but once you have this code, all you have to do is put in the corresponding numbers and bam, you will get your p-values. And in this case, our p-value was 0.0001. So that is how you can get the exact p-values out of R, and I strongly encourage you to give it a go. Come on, try it, try it.